Okay, so we're going to continue with breadth first search. We briefly we gave an overview of it last time, but just to remember, to remind ourselves, basically you explore all the neighbors first. So you explore close vertices before you go deeper into the graph, thus the name breadth first search. In contrast to depth first search, where we used a stack to keep track of our breadcrumbs, we're going to be using a queue to keep track of our breadcrumbs. Because a queue is going to be first in, first out. So if we explore things that are close, we want to make sure that we do it in that order. Say all the vertices that are a distance 1 away. And then we want to make sure that we come back in that order to explore their neighbors, which are now a distance 2 away, right? And that's why we're going to use a queue instead. You still keep track of similar artifacts. For example, vertex color. Initially, everything is going to be a white vertex indicating an unvisited vertex. Then you color it gray, which means that it's become visited. And then once you're done with it, once you processed it, then it's done, right? And you color it black. You also keep track of discovery times and finish times. Now, I put a question mark here because when we actually go to look at these things, you'll find out that the finish time is not all that important because first in, first out queue, it's going to be the exact same order. All right. So I've got the same graph from before. It's an undirected graph. We'll go ahead and do the directed version here in a second. And let's go ahead and walk through a BFS. Now I'm going to draw my queue down here. I'm also going to keep track of vertex, its discover time, and its finish time. Okay? A, B, C, D, E, F, G, H, I. And like we explored last time, which order do you go in, right? Well, you can go in lexicographic order. You can go in, like in your homework, you're going to go, sometimes you'll go in weighted order. Sometimes you'll go in lexicographic order. We'll go ahead and go in lexicographic order, but we'll go ahead and start at A, okay? So when I start at A, I NQ A, I color it because it's now visited, and I'll go ahead and timestamp that as 1. So my discovery time on A is 1. Now I look at the entire neighborhood here, which is going to consist of B, C, and E. And those are all going to be NQ'd in, say, lexicographic order. So B, C, and E all come in. And they're discovered in times 2, 3, and 4. 2, 3, and 4. And they all become gray as well because I've just NQ'd them. Well, I'm done with A, having I process it, and so my finish time here is going to be, say, 5. Color black, and I DQ it. Right? So this is the front of the queue, and this is the end of the queue. Things go in here, and they come out here. Okay? Now, by going in this order, this means that I'm able to keep track of my breadcrumbs. Where do I go next? What's my current vertex? Well, I peek at the queue, and I see that B is next, right? Because it was in the neighborhood of A, and it's lexicographically least. So I look at its neighborhood, a neighborhood consisting of A and C, which is a black vertex and a gray vertex. So neither one of those gets NQ'd, and I don't increase anything. I do increase my counter, though, and I am done with B. It's the finish timestamp is 6. Color it black, you're done with it, and B comes out of my queue. Okay? Next iteration, I pull out, I peek at C, and I look at its neighborhood, which consists of A and B, which are both black vertices and visited and done. Also, E is a gray vertex, so I don't NQ it, but I also have F and I. I will NQ those in that order, 6, 7, and 8 in lexicographic order. So 7 and 8. Okay. And those become gray. And at this point, I'm done with C. I DQ it, and I've got my counter now is at 9. Right? So C's finish stamp is 9. On the next iteration, I've got E. and I look at its neighborhood, well, we've got a couple of black vertices here, but otherwise we've got 3 white vertices, unvisited vertices. So let's go ahead and enqueue those as D, G, and H in order. And that'll be where it was 10, 11, and 12. So 10, 11, and 12. And those all get colored out as gray. Okay? And then E is done. And its timestamp now is 13. It's colored black, and I DQ it. Okay. Next iteration, in fact, all next iterations are going to be F, I, D, E, and H. You're all done, essentially, because there's no either black or gray at this point. But let's go ahead and timestamp them. It's going to be, the next one out is going to be, did I lose my D? No, D is over here. So F ends up getting, there's 13, 14. 14. Then 15. F is 14, 15. Then 16. D, G, 17, and 18 as a final one. 18, 17, and 16. At which point I've popped, or DQ'd, DQ'd, DQ'd. All of these are going to end up as black. All right. So there's my discovery time. There's my finish time. What if I resorted these as discovery time? What would you see as finish time? So what would the first one be? It would be A. What would the first one be here if I ordered them by finish time? It would also be A. What's the last one that I discovered? What's the last one that I? What's the middle one? I have 2, 3, 4, let's say 10. And then 4. The next one would be 7. The fifth one would be the fifth one. 2, 3. Then what? The fifth. So if you reordered them, what order are you going to get in this? Exactly the same. Why? Because I used a queue, first in, first out. If it's discovered at position X, then it's going to be finished at position X. Right? If it's the Xth one to be discovered, it's also going to be the Xth one to be finished. So for that reason, maybe finish timestamps are not all that useful. But you can go ahead and keep track of them if you want. Right? Let's do this again, but let's do it on a directed version. Okay? So we'll go ahead and this time I won't do the finish timestamps. We'll just go ahead and go with the discovery time. Right? And I won't increment my counter on both of them, so it'll just be 1 through 9 instead. I will go ahead and keep track of my queue over here. I'll go ahead and start at A. Now, with this orientation here, the neighborhood is different. You can only go to B and C. So when I NQ A, then I NQ B, and I also NQ C. Right? This one is gray. Its discovery time over here was 1. Its discovery time on B is 2. C is going to be 3. Right? A, B, C, 2, 3. And then I, of course, DQ A for the next iteration. I'm looking at B. Well, again, its neighborhood here is only C now instead of C and A. But it's gray, so I end up not doing anything. I end up, or adding any more at least. I end up DQing B and moving on. So I've got C now. I look at its neighborhood, but everything is an incoming vertex except for this. So this is the only thing in its neighborhood. It's unvisited, so we NQ it and discover it at 4. Gray. DQC and color it black because it's finished. Next iteration, I'm at E, and I look at its neighborhood, which includes A, D, G, and H. Only these 3 are unvisited white vertices, so D, G, and H. And those have discovery times of 5, 6, and 7. Right? 5, A, B, C, D, E, F, G, H, I. F was, or G was 6, H. There we go. So I end up, I already enqueued those, and then I dequeue E because I'm now done with it. But all these are gray now. There we go. D is the next thing in the queue. So I look at its neighborhood, which is empty, and I just end up dequeuing it, coloring it black, and it's done. Likewise, G has a non-empty neighborhood, but it's already a visited vertex. So we end up coloring G black, dequeuing it. There we go. At this point, we look at the neighborhood of H, and we discover I at timestamp 8. Color it gray, enqueue it. And H is done, so we color it black, dequeue it, and we go on to the next iteration. I is dequeue. Its neighborhood here only has one black vertex. It's already done. We end up coloring I black and dequeuing it. Except, are we done exploring the graph? Nope. What else do we have left? F. So we will restart this entire algorithm. Right? And we'll enqueue, if there are any white unvisited vertices left over, we go ahead and enqueue them and then start the process over again as F as our starting point. Again, it's gray. It gets colored because there's no neighborhood, and so we end up timestamping it as 9. Right? So we'll come back and look at the other artifacts that you can build from those in a second. But let's go ahead and codify that as a process. So here's our breadth first search algorithm. And like depth first search, I'm going to go ahead and just do the main iteration. If you need to, with a disconnect undirected graph or with a direct graph with sinks and sources, you may need to restart this main algorithm over and over again until all vertices have been discovered or visited. So our input is going to be, again, it doesn't matter, graph, undirected graph, directed graph doesn't matter. A graph, G equals V comma E. And I will go ahead and specify an initial vertex. Call it V, right? In V. When I did first search yesterday, I made that as part of the algorithm, and I made it so that you arbitrarily chose one. Right? Again, if you're going to go in lexicographic order, or if you're going to go in weighted order or something like that, you can do that as well. I will go ahead and create a counter here. I'll start it at 1. Right? And I will go ahead and initialize a queue. Not a priority queue, just a regular old queue. Right? I will mark V with count, timestamp it basically. I will color V gray. And again, you've assumed that everything is white, unvisited, or if this is part of a subroutine as a main routine, you've done that outside already. It's discovered. Then you enqueue it. So q.enqueue V. Right. This is all the initialization. Now we're going to go into a while loop similar to DFS, that while there's still stuff in our queue to process, we need to continue the processing. So while queue is not empty, we will continue. I'll look at the thing at the front of the queue, the next thing, right? Queue.peak. That gives me my current vertex, just like DFS did. X is where we currently are. We then look at the neighborhood, okay? So for each neighbor, Y, in ends of X, right? This is the neighborhood of X. If y.color is equal to white, in other words, it's unvisited, and we want to ignore those gray vertices. We want to ignore those the finished vertices. Count plus plus, right? So that we when we timestamp this and put it into the queue, we've got a new time counter. We'll mark y with count, and again, this is discovery time. And if you want to keep track of finish time, though, that's later, but again, it doesn't buy you anything. It's the same order. Q.NQ, in other words, add y. And that's the end of your exploration of the neighborhood. You've NQ'd everything that X is connected to. At this point, you go ahead and process it. So Z, I could simplify this a little bit. Q dot pop or DQ. All right. Count plus plus. If you're, you know what? I'm not going to do with I'm not going to do a processing count at all. Again, it doesn't buy you anything. Z dot color is equal to black because it's now done. And process. I'll go ahead and do it over here. Process Z. There we go. You could, if you really wanted to, you don't have to peek. You can go ahead and DQ it right away, and then process it right away, and then go on to its neighborhood. It all depends on what you want to do with it. Right? It's going to be the same exact order. But there's breadth first search. Extremely simple, and again, you can even simplify this even further. And keep track of what you want. Ignore what you don't. If you don't want the count, fine. If you don't want if you do need the colors in order to keep track of what you've seen so far, so that you don't revisit a vertex over and over and over again. All right. Okay. Let's come back to these examples now and try to build something that was similar, that we built similar to DFS. We built a DFS tree. Let's go ahead and build a BFS tree. Similar to the DFS tree, we're going to have tree edges. Those are edges that were traversed to add things to the queue. So when I went from A and I visited everything in its neighborhood, all of those are going to be tree edges. Right? Let me go ahead and mark them actually, like we did last time with red. So when I went with A, I went to C, I went to B, and I went to E. Those are going to be my tree edges that are colored red right now. Okay? So let's go ahead and build that over here. A was connected to B, C, and E. And I'll go ahead and go in lexicographic order left to right. Those are all my tree edges. There we go. Off of E, I went to F and I. B, I didn't do anything. Then off of C, sorry, F and I. All right. Then off of E, I went to D, G, and H. Off of E, D, G, and H. There we go. That's all of them, right? Yep, that's all 10 of them. All right. So I'm not going to pull out the old diagram, but what do you notice about this BFS tree versus the DFS tree that I took the entire page to draw? much more shallow, right? And that's because of the nature of the search, breadth first search. We're searching out in a radial pattern, right? Closer vertices first, versus the depth first search that went as deep as possible, producing a very, very tall DFS tree. Now, what about the other edges here? The edge from B to C. What kind of an edge would that be in our BFS tree? That's a cross edge. All right. What about G to H? Same, cross edge. And what about H to I? Those are all cross edges. Okay? That's kind of weird. We didn't have any forward edges. Why not? Might there have been a forward edge here, A to H? Could there be? BFS. If there were an edge from A to H, what would have occurred? Well, a cycle, but what else? When we started our BFS at A, then what's its neighborhood? H would be in that neighborhood. And consequently, H wouldn't be down here, it'd be up here. Right? So, one takeaway from this is that BFS's trees, there are no forward edges, nor, since it's undirected, forward edges and back edges are the same thing, nor back edges. Otherwise, you would have discovered them already, and you'd have an even shallower tree in some regard. Okay? But you can have cross edges. What do cross edges imply? A to B to C to back to A. Or A to C to I over to H and then come back up over there. What does that imply? A cycle. Right? So if you've got even one cross edge, then you've got a cycle. Okay? Let's go back to the directed case. And let's go ahead and build a BFS tree or forest, maybe. You could get a BFS forest with an undirected graph. That just means that you have a disconnected graph. So BFS tree for the directed version. Okay? Well, again, what were our tree vertices over here? From A, we went to B, and we went to C. From B, we can't go to C because we've already visited it. What about, what was next? From C, we could go to E. Well, we can't go to I in this case. That's not going to be a tree edge, maybe. I don't know yet. No, it's not going to be. And then these three were discovered. And then finally, this one was discovered. And then this one is not a tree edge, because, and as we'll see in a second here, but it is going to end up being a forest like last time. So let's go ahead and draw the BF tree resulting from this. A went to B and C. And I'll keep the orientation there. E. And then E went to D, G, and H. And then H went to I. Okay. Finally, we've got A, B, C, D, E, F. F sitting out here by its lonesome. Okay. What about the non-tree edges here? E goes to A. Where does that look like over here? E goes to A. What kind of an edge is that? Is it a forward edge, a cross edge, or a back edge? That's a back edge. So you can have back edges. Okay. What about going from G to H? G to H. What kind of an edge is that? cross edge. And going to the last one, or a couple more here, I guess, I to C. I to C. What kind of an edge is that? Also a back edge. And F to C. What kind of an edge is that? That's also a cross edge. Because it's not an ancestor, it's not a descendant. I think we got them all, right? Yeah, 1, 2, 3, 4. Yep, that we got them all. Okay, so some observations about this now. You can have back edges. Back edges. Edges are possible. And in fact, what does a back edge imply? I can go from A down to some descendant, I, and then back up, or I guess E, and then back up to A. I can go from C down to some descendant, and then back up to C. That implies a what? A cycle. A directed cycle. What about forward edges? We didn't have any in this example, but is it possible that we could have forward edges? Could I have a forward edge, say, from A down to E? What if I had an edge going from A to E? That would have been discovered in the BFS, right? And it would, then E would be up here, shallower, and it would be, that would be a tree edge. So still not possible. Okay. What about cross edges? Cross edges can connect siblings. They could connect, distant cousins. They could connect between components. Okay? But do they necessarily imply a cycle? Like they did with the undirected case? E to G to H, back to E. Is that a directed cycle? Nope. So cross edges may or may not imply a cycle. Some additional considerations have to be made there. I think that you can get argue some structure about cross edges, that they can connect. A cross edge can connect from one vertex to another vertex, but they have to be within a certain number of levels. That's not all that useful, but you can use it to bound cycle detection if you want to go that direction. Otherwise, there are much better ways of detecting cycles. For example, in a directed graph, for example, DFS. DFS, it's much clearer when you find a cycle. Okay. So let's take a look again at these two artifacts, the BFS tree and the BFS tree for the directed case. In the original undirected graph here, let me get it. Where is it? Yeah. If I wanted to travel from A to, say, I wanted to go from A to I want to do it in the shortest amount of distance. I could go, from A to B to C over to E to G to H and then over to I. But that would be a path of length 1, 2, 3, 4, 5, 6. Right? Is there a shorter way of doing it? Well, I could go from A to E, then to H, and then over to I. And that's 1, 2, 3 hop over. Is that the shortest distance, though, from A to I? Nope. What's the shortest distance from A to I? A to C, and then over to I. That's the distance. Tell me about the tree. A to I. What's the shortest distance? A to C to I. Guess what? BFS computes that. In fact, from A, the shortest distance to any other vertex is captured in this tree. Right? The shortest distance from A to any of these, well, they're all directly connected. There's only distance 1. The shortest distance from A to every other vertex is at most 2. And the BFS tree tells you how to get there. So another observation here is that for undirected graphs, this only works for undirected graphs. Well, it will work for directed, but with a few caveats there. For undirected graph, the BFS tree provides the single source shortest path. In other words, from your start vertex, from the start to all other vertices. It doesn't provide the shortest distance for everything. Right? For example, what's the shortest distance from I to H? From I to H over here in this graph? Well, just one. They're directly connected. But does that correspond to over here in the BFS if you just look at the tree edges? To get from I to H, what do I have to do? I have to travel all the way up to A, and then travel all the way back down to H. If I just looked at the BFS tree, it would look like that there's a path of length 4. Right? So what I need to do is, if you're interested in shortest paths from I to all the other vertices, you need to start your BFS traversal at I, and then generate the BFS tree with respect to a starting vertex of I. Right? Same thing for directed. Same question here. Going from A to I, what's the shortest distance? How can I get there the quickest? Well, if I go from A to B, what corresponds? As you're going to find a shorter distance over here. Okay? So for weighted, directed, and undirected graphs, if you start your BFS traversal at a particular vertex, the BFS tree or BFS forest is going to give you the best distance there, the shortest distance there. This fails, by the way, for directed graphs. Okay? For example, let's go ahead with this. BFS fails to find the shortest path for weighted graphs. All right? So what I want to do is together here, we're going to come up with a counterexample for this. Okay? And it's actually pretty easy. Keep it to 3 vertices, just 3 vertices. Say A, B, and C. This is the topology that I want. Now, here's the directed version. All right, you can come up with a counterexample for the undirected version as well. But think about this. If it were unweighted, that is, it has a uniform weight of 1 on each one of these edges, then what's the shortest distance from A to B? And what's the shortest distance from A to C? Well, A to B, it's just 1. Right? A to C, it's just 1. Right? But what if I put different edge weights on them? What if I said that, well, actually it's quite expensive to travel from A to C directly. It's going to cost you $5 instead. And I'll go ahead and keep a weight of $1 on each one of those. A BFS tree would end up looking from A would end up looking like this: A to B at a cost of 1, and then to C at a cost of 5. And then this would end up being a cross edge that would not show up as part of the BFS tree, except for, unless you drew your cross edges. Now, is that the shortest path from A to C? What are the shortest paths from A to B? Well, it's just 1. What about A to C? Well, if you went from A to B and then over to C, then it just costs you 2 versus 5. You're trying to minimize the distance there. So there are plenty of situations in which this algorithm is going to fail, and that's why we need some additional algorithms. We're going to talk about shortest distance algorithms, both Dijkstra's algorithm and Floyd's algorithm. We'll do Floyd's last because it's a good segue into the next topic, which is. But the takeaway here is DFS is perfectly fine for unweighted and directed graphs. If it's weighted and the fails to find you the short paths. So far? No? Then, put that over there. Then let's go ahead and use the algorithms that we've found so far and start discussing some additional applications. So more applications. Well, there are some very simple applications that you can do. You can do, there are connectivity questions. Connectivity properties. For example, just very, very generally, given two vertices, x and y in V, determine if there exists a path from x to y, right? Directed or undirected, right? This is the squiggly line, squiggly arrow line right here. That's my notation for a path. Directed or undirected. All right? Now, before we go on and look at others, what I want to do is I want to give you a preview of something we've implicitly done up to this point, but a preview of what we're going to explicitly do later on. This is a decision problem, or version. This is the decision version of this problem. What's the answer to this question? Determine if there exists a path from x to y or not, right? Think about an oracle, right? And you've got a graph, you've got these things in an oracle. If you're not into Greek mythology or whatever, what is an oracle? Kind of like a psychic, right? It was something you would ask, an omniscient being, right, that you could ask questions to. You could ask questions and they would immediately come back with an answer. Now, in Greek mythology, or Greek tragedies, they were used as a trope, basically, to they would give you answers, but they would give you incomplete answers, like yes or no. Like, will I be able to defeat the army? Yes, you will. Not giving them the full story that yeah, but you're going to defeat the army, but you're also going to die, right? That was the Greek tragedy. That was the trope of Greek tragedies, that the hero would always have incomplete information leading to their downfall. And the oracle gave them that information. So this is kind of like the oracle. If I had these three things, G, X, and Y, and I gave them the oracle is just going to answer yes or no. That's the decision version. It's just a yes or a no question, right? Now, in programming, what does this correspond to? What would a function look like? What would the return type be in programming? It's going to be true or false, right? Which is great if you just want a true or false answer. Does there exist a path or not? Well, what about a little bit more information? You don't want to just know if there's a path or not. What else might you want to know? You would maybe want to know the length, right? If I gave you, so there's an optimization version. All right? It's not a yes or no question, but it's a value question, right? It's the given G, X, and Y in V, output Now we've actually got output here. The length of the shortest path, say. Of course, if you want to do optimization, you could also do the longest path. Which is intractable. That's a very difficult problem. This is actually a very easy problem because we've got BFS to do it in some cases. We've got Dijkstra's algorithm that we'll look at in a bit. Right? So this is the the optimization version, right? It's the value. It's the length of the best solution. Maybe I shouldn't even say length. It's the value of the best solution. Okay. Well, maybe that's not all the information that I want. I want even more information. You told me, yes, there exists a path. Great. What's the length of the best one? 5. Does that help me get from A to B to C to D to E? Does that help me get from my X to Y? If I knew that the best way to get from X to Y is going to cost me $5, does that tell me how to do it? No. So we also have a functional version. Right? It outputs the best solution, not just the value of the best solution. It actually outputs the best solution, period. Right? So given G, X, and Y in V, output the shortest path P from X to Y. Okay? Now, again, as a preview of what we're eventually going to do, what would these look like programmatically? Right? What about the optimization version? What would the return type there be if this were a program? Up here, the decision version, it's a true-false. In other words, a Boolean. With the optimization version, it's a value. So the program would output a what? Or the function would output a what? Well, let's just go ahead and assume that they're all integers. Right? An integer. 5, 7, 3. Right? If the output is the functional version, it outputs the best solution. What would the program actually output? I don't know, think Python if you want to. I want to get from X to Y. Tell me how to get there. What are you going to need to tell me? Go from X to this vertex over here. From this vertex, go to that vertex. From that vertex, go to that vertex. From that vertex, go to Y, and you're at your destination. So what would the program output? Well, in this case, maybe a list. Right? So let's think about a Pythonic way. Let's go ahead and think more concretely about these things. What if I had these functions? Def exists path, and it took G, X, and Y. Sorry, there's no colon there. Right? Dot dot dot. I don't know how to program that. Right? You know how to program that. Right? But let's just assume that it's there. Length or shortest path length. We'll say G, X, and Y. Dot dot dot. This returns a Boolean. This returns an integer. And finally, def get shortest path. G, X, and Y. And suppose that that's a list. All right? Now, what I want to do with this exercise is, can I use one of these things to solve the other? Right? Again, I don't know how to write this. I don't know how to write this. I don't know how to write this. Let's go ahead and write. Let's just assume that somebody's written two of the other ones for us, and we'll write the third. All right? So, for example, suppose that somebody's written exists path for us. It's work X or something. Now, this function, using that function, get this path. Does the answer to a yes or no question, that Greek oracle, does the answer to whether or not I'm going to win the battle, does it tell me the whole truth? No, it tells me the truth, but it doesn't tell me the whole truth and the necessary truth. Implement this function, not without actually implementing it directly. What if network X this function, right? With the contract that it returns in Python, and there's no null, right? What is the placeholder for null in Python? None. Is that case sensitive? I think it is. Yeah. Just like true and false are case sensitive for some reason, some weird stupid reason. Run none if no such path. Right? Or it could be that the length of the path is going to end up being an empty list or something, or maybe an empty list. Whoever should have the documentation, we could use it. Right? Let me write a function now. Def exists path of G, X, and Y. What does that look like now if I've got access to this library function up here? What should I return? I need to return yes or no. Does there exist a path? Well, if I read a different oracle, I don't know. Yes, here it is. I can't give that to you. Then what do I return? Get shortest path. G, X, and Y. That's going to return a list, or it's going to return none. So if the answer is none, you return no path. If the answer is not none, then I should return yes. Right? So versus none, what do I need to return here? Get shortest path is not equal to none, right? So by using an answer to the functional version, I've got an answer to the decision version. What about shortest path length here? Could I answer this question if I had an answer to this question? What would it be? Here's your, this is the ultimate question, right? I can use the ultimate answer to get lesser answers. Here's the answer. Here's the list. Here's your actual path. Okay, just take the length of that path, the length of that list, and you've got your answer, right? Or go along if it's weighted and count up the edge weights. Right? But it's an interesting question. Can I go the opposite direction? Can I use a yes or no question to find the shortest path? It's not immediately apparent that you can, but the answer is yes. And you'll be doing it on your fourth homework, right? In some form. Right? That's just kind of a preview, though. Right? And by the way, this is fundamental to programming. I talk about this in CS1. Right? What principle is at work here in coding? This is all completely theoretical. This is like halfway between theoretical and practical. The practical side of it is the DRY principle. Don't repeat yourself. Would you go and implement all three of these functions in a library? No. Implement one of them. Then call it with the others. Right? Don't repeat yourself. only implement the most abstract, the most general version of this, and then use that most general version of this to get the more specific versions of this. And with respect to pure theory, we're talking about different versions of problems. We're talking about decision versions, optimization versions, and functional versions. Right? So the takeaway from this is that eventually you'll get into a lot more theoretical stuff like automata and stuff like that. It all has a grounding in practical application. Right? There's some analog to CS coding principles, best practices that can be found in a lot of theoretical stuff. Okay? So that's connectivity problems that you can answer yes or no whether or not something is connected. Of course, you've got, like we've looked at already, shortest path. Shortest path problems. DFS isn't going to help you there. BFS it will help you there, but BFS is only good for unweighted graphs. Okay. Another application would be topological ordering. All right. So for this one, I'm going to remind you of 235 material here. Do you remember what a poset is? What is a poset? Or a partially ordered set. Right? And when I do this in 235, I also take the opportunity to call your attention to what this is called. A partially ordered set is is P, O, and S all put together here. What is that called? It's not an acronym because that would just be POS. But it's not an acronym because you're taking parts of three different words, taking things out, and then shoving them all together. Does anybody know what that's called? Come on. No? It's a portmanteau, I think. That's how you spell it. I'm not sure. But so there's your language lesson of the day. That's a portmanteau. When you take a couple of words, graphs, we call them digraphs. You're just taking parts of the words, beginning of the words, the middle of the words, putting them together to create a new word. That's a portmanteau. So what is a poset? A poset is under a relation that is, for what they are flexive. What else? Transitive. And thought I heard it. Anti-symmetric. Right? And this perfectly captures a lot of, for example, integers under the less than or equal to, that's a total ordering. So a better example would be, say, a power set of a set and the subset relation. Okay? So this is a good 235, since I'm not hearing a lot of I didn't hear many people remember that it was reflexive, anti-symmetric, and transitive. Let's go ahead and review it by looking at something like this. So let's go ahead and create a set here of three elements, A, B, and C. Now the power set of this, this is the power set of S. It's a set of all subsets. And they're going to be related if A is going to be related to B. And these are uppercase and, A and B because they're sets now. If and only if A is a subset of B. Okay? So when I draw the diagram, maybe it'll look more familiar. So there's a subset that is a subset of any other set, and that's the empty set. That's going to be at the bottom. There is a set that is related to from every other set, and that is the original set, A, B, and C. Okay? You also have the singleton sets, A, B, and C. Right? And these are all, the relation goes upward. Right? And we've also got the doubletons. A, B, A, C, and B, C. Okay? Now what about there? These are all related to this set because AB is a subset of ABC, AC is a subset of that, et cetera, et cetera. What are the relationships here? Well, A is a subset of this one. A is a subset of this one, but it's not a subset of this one. B is a subset of the first and the third. C is a subset of the second and the third. Right? We have this nice little diagram here called a lattice, otherwise known for, at least in the context of post sets, it's called a Hasse diagram. Right? It's reflexive. Why? Well, we've got all these self edges on these that I'm not drawing because any set is a subset of itself. Right? Every element over here is an element over here. Right? It is transitive. This empty set is a subset of A, therefore it's an empty subset of AB. A is a subset of AB, and AB is a subset of ABC, therefore A is a subset of ABC. I just didn't draw it because I wanted to simplify the diagram. That's what a Hasse diagram does. A is a subset of B, B is a subset of C, implies that A is a subset of C. And it's anti-symmetric. So here's the real question. What is the definition of anti-symmetric? A is a subset of B, and B is a subset of A, implies what? A is equal to B. Is that true? That's the very definition of set equality. Right? In other words, the relation only goes up. And that's why I don't have arrows going up in the Hasse diagram, because there would be no arrows going down in this relation. Okay? This is a partial order. Some things are comparable, some things are not. B is comparable to these two sets because it's a subset. But there is no comparison between the singleton set B and AC. One is not a subset of the other, and the second is not a subset of the first. There's no relationship between these two things. Right? So, if I have a power set here, one thing that I might want to do is I might want to enumerate them. I might want to sort them. What comes first? So I've got 1, 2, 3, 4, 5, 6, 7, 8 sets here. What comes first? Here, I'll just do it down here. If I gave you all these sets, and I said give each one of them a number and list them out in order. Could I do this? What about this ordering? We'll go ahead and go with this singleton set A, and then we'll go ahead and go with A, B, C, and then we'll go with the empty set, then we'll go with the set B. Does that make much sense? ... Is that a proper ordering? Well, look at the relationships up here. A is a subset of ABC, but is ABC a subset of the empty set? No. Does it make sense to put the empty set after these sets? No. So maybe to make a little bit more sense of this, maybe we want to start with the empty set. What could you, now, with that same principle there, what do we want to put last? The set ABC. Right? Now, what ordering do we want to go in here? Should I go ahead and just start listing out the doubletons? No, because I've got singletons that are related to it. But what about the singletons? Should I go A, B, C? Now, you might be tempted to think, well, A, B, C, that's going to be lexicographic order. Don't think of them as A, B, C. Think of them as object, object, object. I'm not even going to say object 1 and 2 and 3 because that's yet another ordering. Right? So object, object, and object. Is there any way, and this object is not comparable to this object, or vice versa? Does it matter? Go this object and then this object and then this object? Nope. So I could go in any order that I want. B, then C, then A. Now that looks ugly because we're naturally prone to lexicographic ordering, but this is perfectly fine with respect to this relation up here. A, B, C, well, they're incomparable. You can go ahead and do those in any order that you want. And in fact, after I do B and C, I could have gone and done the doubleton containing B and C because I've already enumerated the two things that are related to it, right? And then I could go on and do the other doubletons, A, B, and B, or what did I miss? AC, sorry. There we go. All right. So the order that you go, so this is a partial order. What we want to do is we want to transform a partial order, a poset, into a total order. In other words, I want to write them all out in a consistent manner. We want to impose a total order on the poset, but we want to make sure that we are consistent with the original relation. Right? Incomparable pairs may appear in any order, but comparable pairs will never be out of order. With respect to the original relation. Okay? Sorry, there we go. So the solution here is a topological sort. Right? And all it is an application of DFS. Now, why would you want to do something like this? I've got a roster of students. In any programming language, I want to sort them. I've got all the students here in this class. If I just have, say it's Python, say it's Java, doesn't matter. You've got a student class, okay? And you've got 20 instances of that student built, and they're all in a list. If I called Python's sort method, how would it sort? I called Java's method. How would it sort it? Good questions, right? Good interview questions. Right? If I were still in industry, I'd definitely be asking these questions. Right? If I just had a regular Java, I just had a regular old Java class called student, had a first name, last name, GPA, et cetera, et cetera. And I called collections.sort on an array list of students. It wouldn't even compile. Why not? By itself, is a student comparable? No. How do you make it comparable? You implement the comparable interface, or you what does a comparator do? Exactly, or imposing a order, and there's no way to work. If you don't have a comparator or have made your object comparable in Java, there's no way that it can sort that. It won't even compile. Same question in Python. What will happen? I actually don't know the answer. Maybe a runtime error. You go ahead and try it. You just create a generic student class and call the sort method on it. It might use some internal representation like a hash code or something like that, or it might do its best guess. But can you interpret anything out of that ordering? Probably not, and nothing meaningful at least. If you want to order student objects by last name, first name, you need to write the code to do that. If you want to order them by last name, first name in reverse order so that Zoroaster is at the top instead and Applebaum is down at the bottom, then you need to specify that. If you want to order them by GPA, descending or ascending, that's all stuff that you have to implement. Now, I do know the answer of how you do that in Python. Many of you probably do too. How do you make something comparable in Python? There is no interface. How do you make something comparable? What? You override the magic methods, the equal and at least one of the LT less than, GT greater than, or I think that there's LTE and GL greater than, GTE, I guess, greater than or equal to, right? Those are all magic methods that have no default implementation that I know of. You put one of those in and it magically becomes comparable, right? In other words, what are you doing? You're doing a total order. Again, all this theoretical stuff has practical implications for every single programming language out there, right? All the way down to the basic stuff. A total ordering. How do we actually do it? So, to do a topological ordering, all you do is perform a DFS on, now, an undirected graph is not a post set. It had to be a DAG, right? On a DAG. A DAG is a directed acyclic graph. Because if we had a cycle, then this, in a post set, if I had something like this, it goes to B, B to C, and then C goes back to A. Is that a partially ordered set? Nope. It's not asymmetric. Like, it's not a relationship here, but A goes to B, B goes to C. The would be going that direction. But going around like this, you necessarily have to be anti-symmetric. This would mean that A needs to be equal to B equals to C. It would have to collapse down to a single node. And that, so it can't happen. You can't have cycles. You have to have a directed acyclic graph. Okay? Self-edges, those aren't that important. The interpretation there is if you're at vertex C, well, then you can get to C by just staying there. Right? And transitivity, you can always do a transitive closure, Varshall's transitive closure algorithm, to add the necessary relations. So we'll assume that we have a directed acyclic graph. We will note the finish times, finish timestamps, stamps. Right? Then now oh, yep, that's it. Yeah, note the finishing timestamps. We don't have to reverse it. I'm thinking of something else. And sort in descending order of finish timestamps. And that gives you unordering. And that's it. Right? Very, very simple order and algorithm to give you a linear algorithm to give you a total order. Right? This right here ends up being your total order. Right? Now, in most cases, with actual objects or whatever in a programming language, you don't have to. You kind of do it in reverse. You know ordering that you want, and you establish that ordering. But if you've got just a generic objects with respect to, say, mathematics, then you can you could say with that set example, you can say, okay, not only that, but we want to establish a lexicographic order, and so that lexicographic order would of course establish a total order. But if you've got more theoretical objects, or you just don't know, how do I compare these two students? Well, I know how to compare these two students. I don't know how to compare these two students. Well, I could go ahead and go with topological ordering if I have incomplete information or something. Okay? All right. That is a solution to that problem. Right? I think I'm going to need more time to do the next part. So, and we've got plenty of time tomorrow. So I'll go ahead and, oh, wait, one last thing I will do today is cycle detection. This will definitely fit. Right? In fact, we can leave early after this. Cycle detection. Given a graph G, determine if it contains a cycle or not. Well, how can we use DFS, BFS to do that? Run DFS or BFS, right? And what's your criteria? Well, if you generate the DFS tree and BFS tree, you can, you can find a cross edge or a back edge or whatever, depending on the situation, and then you can say that there's a cycle. But what else could you say? If you encounter, say DFS here, if you encounter a gray or black vertex, gray or black, I'll go ahead and put a question mark there, that was previously encountered, then you can stop and report a cycle, right? Otherwise, if you don't find something that you remember, so cycle detection, very, very easy, right? You can also do disconnectivity, right? So given G, is it connected or not? In other words, is it two connected components? Say a triangle over here and then this component over here, right? There's a disconnected graph here. How could you use DFS to detect this? Perform a DFS, and then a single DFS. And if I perform a DFS over here, at the end of it, all of these are going to end up being colored black. But what about all these over here? They're going to end up being still unvisited white vertices. So if any white unvisited vertices remain, then it means that it is disconnected. Right. Now, disconnectivity has a different meaning for directed graphs. I'll pick it mean for I could have like 5 vertices. Instead of just connectivity, we need a notion of strength of connectivity. And we say that two edges or two vertices, excuse me, are strongly connected if I can go from A to B, then that means that somehow I can go back from B to A. Right? There's some directed path that takes me between these two vertices. They're strongly connected. And if these two vertices are strongly connected, then as far as the topology of the graph is concerned, I can treat them as one component. Because if you can go from A to B and you can go from B to A, well, any nodes along that cycle means that they can communicate with each other. If you think about them as nodes in a network communication, A can get communications to B and B can get communications back to A. Something would, two vertices would not be strongly connected if that were not the case. A can connect to B and send messages, but maybe B cannot send messages back to A. Those are only weakly connected. And maybe it's a situation where neither A nor B can talk to each other at all, in which case now you've got a complete disconnectivity with respect to directed graphs. Right? And that's where I'll pick it up tomorrow.